car going 20 meters per second locks up its wheels in an attempt to stop quickly. If the coefficient of kinetic friction is equal to 0.800, how far will the car slide before coming to rest? So I'm thinking for this question that I'd like to do a force analysis to find what the car's acceleration, or maybe I should say deceleration, is, and then use that to try to answer the question of how far it slides given its initial speed there. So in that sense, like if I'm thinking about, I don't know, maybe I can draw a little picture here of two wheels without a car. Yeah. All right, this is my new version of a car. My older ones were less good. So anyways, I have a car, you know, and what information do I have? I've kind of got like a 20 meters per second. I guess I can put that in this picture here. I know it's locking up its wheels in an attempt to stop quickly, so I know it's accelerating dramatically in the opposite direction than it's going. I'm inclined to kind of put here that this is a V naught, and you know, just to make clear that it's not going to be maintaining that velocity. Let's do the free body diagram. So a lot of this free body diagram I think should be reasonably straightforward. We're definitely going to have a force of gravity. We're going to have a normal force, and there should be a friction force in the direction of the acceleration, which really represents kind of that deceleration of braking. And then this is clearly, I think, an F equals ma type of situation. It's not an F net equals 0 because we've already identified we're going to try to find acceleration here. Clearly, acceleration is what we want. So I'm writing F equals ma. And, you know, we're really saying here we've got these three forces. And this may be, I don't know, I was tempted to skip this step here, writing this. It's kind of a formal process that I've been demonstrating in a lot of these videos. To do it, I'm trying to be as consistent as possible, and yet it is true that the more you understand about forces, at some point you realize that for certain problems maybe you can skip a step. And in this case, in particular, if I'm going to look at just like what are the x components here, I know that Fn and Fg don't really matter, so I could have maybe gone straight to this and just recognized, in some ways I could have maybe just said force of friction is equal to mass times acceleration. Anyone else notice that the mass wasn't given to me? Uh-oh. Could that be a problem? Well, we'll find out. Another possible issue is I said I'm doing the x components. Maybe somebody really into x always pointing in the right direction could have said, shouldn't this one be minus? Well, then this one should be minus as well, but maybe we can just pretend and say we did and just leave it as this because we know they would cancel out, right? Those minus signs, you could switch them on both sides. So we do have this. But we know, okay, this is a kinetic friction situation. And so we definitely know, I'm going to add here into the mix at some point, that this force of friction will definitely be equal to, this was like the big discovery that Coulomb made at some point, is regardless of how fast this car might be going or at what point in the braking it's happening, guaranteed that force of friction is equal to the kinetic coefficient of friction times the normal force. Of course, then this begs the question, like, well, do we need to know what the normal force is? And maybe what we could do is, like, if we add the y components of this F equals ma analysis, we would see that it is normal force minus gravity force is equal to 0. There's no vertical acceleration. I hope that's obvious enough, but these two pretty much just came from this picture right here. But that implies that the normal force is really equal to the gravitational force, which of course has the magnitude mg. So maybe I could actually go in here and say, okay, force of friction therefore is equal to mu sub k mg. And then if I went, you know, so maybe to be clear, I'm now kind of messing around with the math and just trying to get to a solution. And this is where things get a little bit muddy. But really, these three things, these two, and this statement about kinetic friction, that was the point at which all the physics analysis was pretty much done. And at this point, I'm really just, you know, working with these things, trying to get my way to a solution. And I'm doing things, you know, there's no real like method to this. It's something you just get practice with. Substitution tends to be a common thing here. So I'm going to substitute this expression that I have for the force of friction into this first expression that I got. And that's going to give me, I guess I'll put it over here. So it gives me a little more space down here if I need it. That's going to give me that mu sub k mg is equal to ma, and the masses then can cancel. Oh, whew, I was worrying about that mass not being given to me, but it just canceled out. So I think that saved me there. And then so this implies that, wow, could it really be that simple? This is kind of amazing, I think, that it amazes me every time I do this. The acceleration is just equal to the kinetic coefficient of friction times the free fall acceleration. That kind of gives you a new interpretation that, like, on a level surface, if an object is sliding, you can look at this coefficient of friction. It's kind of like, you know, you can even say, like, if this point 8 is like 80%, you could say an object can decelerate maximum, or, well, not really maximum, just does it at 80% of free fall, right? Anyway, so that would let us actually calculate this if we want, right? Because we could say 0.8 times 9.81 meters per second squared. And let me consult my calculator again here. That gives me 7.848 meters per second squared. Now I've got this little tiny region here to finish this problem, and I think what I'd like to do is I'm going to use that timeless equation from kinematics. And so that one was like v squared is equal to v naught squared. Maybe I can make this an explicit minus 2a. Why did I do that minus? Well, I know the car is slowing down, so it's the acceleration is pointing in the negative direction for a displacement in a positive x direction. So I felt comfortable putting that minus sign in there, recognizing the final velocity is going to go to 0. So that would mean that v naught squared, maybe I'm doing a couple too many steps here, but I've got little space here. But I think it's clear that with that 0 on the left side, that means really these two things in the difference here must equal each other. And maybe stated more algebraically, I think I added this term, the 2a delta x term, to both sides. And I'm really trying to figure out that distance, right? Like, ultimately, I want to figure out, this is where finally a solution, I think, presents itself, because I want to solve for that delta x. So doing a little more algebra, I find that delta x is equal to v naught squared over 2a, and I already found a number for 2a, and I didn't round it off at all, actually, which is good, I guess. But anyways, I can now put in that 20 meters per second squared divided by 2 times the 7.848 meters per second squared. Oh boy, this is barely leaving me enough space. I don't know if I can squeeze it in there. My calculator says 25.4841, etc. But that's like 25.5. So maybe I can squeeze in a little 25.5. And the units should be in meters if I did this all correctly. So I don't know if I've got enough space to box that there. But 25.5 meters is what I'm saying. There it is.